Okay, now we're on to conditionals. So this is the assignment that you were given today. I'm not going to do the full thing, but I am going to run through the basics of it. So remember that a conditional is an if-then statement. The if part is the hypothesis. So if, well, it makes sense, right? Because your hypothesis, that's in science, that's your guess. The conclusion is your outcome. So here we're saying if, that's where we put in our hypothesis, and then the then is the conclusion. So we look at number 1, and 1 and 2, we're just breaking it up into hypothesis and conclusion. So number 1 says, if the product of two numbers is 0, then at least one of the numbers must be 0. So we know that the hypothesis is the if part. The product of two numbers is 0, because that was our if, right? And then that's our conclusion. That cues us in that it's our conclusion. Then at least one of the numbers must be 0. That's it. So that's just separating the hypothesis and the conclusion. Where it gets a little bit trickier is down on like 3, 4, and 5, where you have to create your own if-then statement. Because the statement we have here is, a rhombus is a quadrilateral with 4 congruent sides. And what a lot of people like to do is simply throw if and then into there. If a rhombus, then a quadrilateral with 4 congruent sides. And while that may be true, it's also really clunky. Or they'll just split it half and half. If a rhombus is a quadrilateral, then it has 4 congruent sides. And that's not what we're looking for. We're looking for, if an object is a rhombus, then it has 4 congruent sides. If they finish the marathon, then they will get a medal. Your hypothesis is that what must happen in order for the conclusion to occur. So a rhombus, that if it's a rhombus, that's our hypothesis. Is it a rhombus? Yes or no? If it is, yes, then it's a quadrilateral with 4 congruent sides. Our hypothesis on the next one, if they finish a marathon, this is a conditional because it's setting a condition on the conclusion, if they finish the marathon. If they don't finish the marathon, then none of this is really relevant. But if they finish the marathon, then they will get a medal. Okay. So remember we talked about inverse, converse, contrapositive, and biconditionals. So here, I forgot to do the biconditional on this one, so I'm going to say it. I'm not actually going to write it down. So if a number is a natural number, then it is a whole number. Well, first we need to define natural number and whole number. A whole number, this is true. So whole number are counting numbers. 1, 2, 3, 4, 5, 6, 7, 8, 10 billion, 30 trillion, whatever. And 0. So 0 is considered a whole number. Now, natural numbers are also called counting numbers, and those are just the numbers we count. So 1, 2, 3, 4, 5, blah, 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 blah. So notice that the set of whole numbers is basically the set of natural numbers plus 0. So every single natural number is part of the whole number set. So that's why it is true. That's why when we say if a number is a natural number, then it is a whole number. Just like we could say, there are a lot of things we could say, but we're just going to stick with this. So because all natural numbers are also whole numbers, this is true. So remember that the conditional here is if P, then Q. The inverse is if not P, then not Q. And so that would be, if a number is not a natural number, then it is. So if a number is not a natural number, then it is not a whole number. Well, the problem with that is 0. 0 is not a natural number, but it is a whole number. So even though you have from 1 to infinity are both natural and whole, which means of all the numbers we can come up with that are whole numbers, 99.9999999999999% of the time that's going to be true, but because of that pesky little 0, because of that one instance in which it is not. What? I'm right here, Cleo. She's literally sitting just out of arm's reach, yelling at me for not petting her. So anyway, but because we have that 1 0 of all of the possible numbers, of all of the possible positive counting numbers, billions and billions and trillions and quadrillions and quintillions and words with Googleplexes, all of those make it true. But because we have one single number, 0, that doesn't make this statement true, the statement is false. And again, it is either always, always, always true, or it is false. The converse of a statement is when we switch around the hypothesis and the conclusion. So now this would read if Q then P. So we go if it is a whole number, if a number is a whole number, then it is a natural number. And again, we're going to go false because of 0. The only one, we have one example where it's not true. So it doesn't matter how many times it is true. If it's not true even once, it's false. Then we have our contrapositive, which is where we go if not Q, then not P. So we not only flip it around, but we then negate it as well. And this says if it is not a whole number, then it's not a natural number. And that's true, because all natural numbers are also whole numbers. So if we know that it's not a whole number, we know it's also not a natural number. So, biconditional. I didn't write this down, but a biconditional, that's it'll look like this. P if and only if Q. And so here we would write down if, or not if, we don't have an if-then statement when we have a biconditional. That's a really common mistake, and one, frankly, that I just made. So when we have a biconditional, we just make the statement. We don't have an if-then, but we do put that either we can write it out if and only if, or if we're feeling special, we can write it out as IFF. So in this case, we would write a number is a natural number if and only if it is a whole number. And that would be false, because when we're looking at the truth value of a biconditional, we need both the conditional. If it's a natural number, then it's a whole number, true. And the converse, if it's a whole number, then it's a natural number. Well, that's false. So because they're both not true, the biconditional is false. And then on that back page, so we have P, you have a library card. Q, you can check out books. And then so what we have here is kind of the jumbled up conditional, inverse, converse, contrapositive, or biconditional. So the first one we have is your standard if P then Q. This would be the conditional. And that would be if you have a library card, then you can check out books. And that is our conditional. So I'm going to be honest, I'm not exactly, just had a little issue with my computer, so it stopped recording. So I'm not sure where we left off, but I think it was somewhere in there. So if P, then Q is your standard. If you have a library card, then you can check out books. And that's the conditional. Now notice here, what we are not doing is assigning any truth value to it. We're simply practicing with the notation and knowing how to put together conditionals, converse, inverse, contrapositives, and biconditionals. So the next one reads, if not Q, then not P. So notice here that we switched it around and negated it. So we'd go, if you cannot check out books, then you do not have a library card. And that would be the contrapositive. So then for 10, 11, and 12, what you're going to do is fill out what those statements are and then identify what they are. Now, in your notes, you should have what makes up the inverse, converse, contrapositive, and biconditional. So this shouldn't be too difficult for you. And that is it for the second part. So I'll see you guys in class tomorrow. Or I guess later today, given the time. So, see you then. Bye. Oh, it's actually only 11:30. So yeah, still tomorrow. Good night.